Hi, this is Thomas from Apex Game Tools. This is the third video on height navigation, and in this video we'll be looking at how you can customize the changes that we made to height navigation in Apex Path 2.1. If you have not already seen the second video that details these changes to height navigation, you should watch that before you watch this. So, before we actually get to see how you do these customizations, let's just quickly touch on why you would want to do that. Now, there are two main reasons. The first has to do with the included height samplers. Now, by default, we have this default height navigator, and it has a number of height samplers dependent on the chosen sphere collider and the height navigation settings. Now, if for some reason these samplers do not fit your needs, you can write your own. One example could be if you're using mesh colliders. In this case, I've used the mesh collider for my unit, and mesh colliders provide the same options as box colliders do. In fact, mesh colliders are treated as boxes in the default samplers. Now, in this case, we have a triangle unit, and it is represented by a box. That is not a very good representation of a triangle, so in this case I might want to create my own sampler that would actually sample points more appropriate to a triangle. Now, the second reason that you might want to implement your own height navigation has to do with the pending issues that we have with height navigation. As mentioned in the second video, we have solved the issue with units floating above the ground when they move up heights. However, we still have the issue where, especially box colliders, when they need to align themselves with their elevation, they do not properly do so. This problem is not easily solved. Well, it's not easily solved in a generic way that will fit all different scenarios. So for that reason, this has still to be implemented, and we will probably also implement it at some point. But for now, if you need that, you are left with the option of implementing it yourself. So that means replacing the default implementations. So let's look at the different options we have. Now, as mentioned, we have this default height navigator. One option is to replace this altogether and have your own height navigator. The second option is to still use the default height navigator, but create your own custom height sampler. So you would basically choose custom, and then you would provide your own height sampler for use with the default height navigator. So let's look at these options in code. The first option is to replace the height navigator. To do so, you need to implement this interface. It has one property, as you can see, and two methods. Gravity simply allows you to return, or you should return, the current gravity acceleration. Then you have the main method here. This method provides an output, or it changes basically the output of the steerable unit component to include height navigation. So it includes the Y component. And then finally, we have the cloning method that allows the height navigator to clone itself from another height navigator. Obviously, this middle one is the main method and the method of most interest. And the way we're going to look at this is to look at the default height navigator and see how that is implemented, so that you can have an idea of what you actually need to do if you need to implement your own. So if we jump to that, we are just going to quickly go through what it does. Now, as mentioned, the point of this is to actually have the unit navigate heights up or down. The steerable unit component will typically not include a Y value in its velocity. The steering components built into Apex Path and Apex Steer only navigate in the XZ plane. You can actually provide your own components that also add a Y value if they are flying or whatever, jumping. But usually this velocity that you can get here will only contain X and Z values. So now the responsibility of this method is to actually add the y component that will tell you the unit that it needs to move either up or down according to the terrain. So yeah, the first thing is to get a hold of that. The next thing is to actually get the height difference using the height sampler. Obviously, if you create your own implementation, you can create your own height samplers as well and do this differently, whatever. But you need to get the height difference between where the unit would be if it moves just straight ahead without doing any height navigation, and where it needs to be to follow the terrain. So that is the height difference that it needs to use. Next up, it handles gravity. So if you don't want to use gravity, or if you want to implement your own gravity, or if you want to use physics gravity, you would do this differently, obviously. So the next thing is actually to change this final velocity to include the y component. We then clamp it to the effective maximum speed so that we don't have the unit moving too fast, because it needs to scale heights. It still needs to keep its current speed, or at least that is how we have implemented it. And finally, we return this result as an output. Now the output also includes a value that tells us if this unit is considered grounded or not. So that's basically all you need to do to implement your own default height navigator. Obviously, the complexity of implementing this method, well, it's dependent on what you want to do. So let's look at the next option. The next option was to simply keep this default height navigator but provide a different height sampler for use with your units. To do that, you need to implement this interface called iUnitHeightProvider. This has one method, getHeightDelta, which will return the delta, as mentioned before, between where the unit would be if it just moved straight ahead without any y differences, and where it actually needs to be to follow the terrain. So let's, before we actually look at how you would add this component to your unit, we will just look at how this can be implemented. We will use one of the existing one of the existing providers for this example, and in this case we're just going to use the raycast spherical 3-point provider. Now, as you can see, this one is actually not a mono behavior. It is just a simple class. It does not need to be a mono behavior. In fact, there's no reason for it to be. So it's just a simple class. You just need to implement this interface. So let's look at how this method is, what this method does. It does quite a lot, and we're just going to briefly go through the different things it does. Now, it is supposed to sample some points. In this case, we have 3 points we want to sample. So the first thing I do is I actually find these 3 sample points. I do that using some points I've created in my constructor that are in local space, and then I just transform those points so that I have some points, the point in front of the unit, the point in the middle of the unit, and the point to the back of the unit. These are the points I want to sample the height at to determine where I want to be. Now I also add a look ahead, because if I just look at where I am now, that is not actually going to work, because I want to know what the height is at where I am supposed to be in a frame's time. So I add a look ahead that is, for the most part, how I'm going to move. So this is the full velocity of the unit current, full velocity, times the delta time. So that's where I'm going to be, and I basically project these points to that position. We then initialize a different number of variables to support the next part of the logic, and then we do the actual height sampling. So this, using raycasting, we sample the different heights to find the highest point that the unit will hit when it moves. And using that highest point, we're just going to skip this. Using that highest point, in this case we are using a sphere. Obviously, if it is another type of collider, you would do this differently. This is a sphere, so where we actually need to find the closest point on the sphere that we want to be on the ground. So what this ends up being is that we find the delta, that means the difference between where we would be if we just moved straight ahead and where we want to be according to the terrain. We do that by finding the difference between those two values. That is the delta value. That is the value we move either up or down in y. And that is what we return. Now this bit here has to do with checking that the value that we've found does not violate the height capabilities of the unit. Now obviously when you have a unit move, the Pathfinder would never actually give a path to the unit that would violate these height navigation capabilities, but if units are moving in groups, they may actually avoid each other or be pushed by others or so forth. That would actually make them move into the path of some terrain that they need to evaluate, these terrain that is actually outside of their path. So this ensures that if that happens, they do not actually climb terrain that they are actually not allowed to climb. So that's basically it. The gist of it is this method needs to return the difference between the difference in y value between where the unit would be if it moved straight ahead without doing any height navigation and where it actually should be in terms of y to follow the terrain. Now we skipped one part in the middle here, and I'm actually just going to touch on that briefly just to explain why this is here. When a unit moves, obviously the front of the unit hits, typically at least, it moves with the front first. The front of the unit hits the height first. So let's, for example, say that we have a mountain. So that is a steep slope ending in a summit, and then we have a steep descent. Now when the front of the unit hits this summit, the unit actually has to continue rising because it has not actually cleared the summit with the bottom part of it. So it needs to actually rise until it has completely cleared the summit before it actually starts its descent. Also, you could, if you have very big units, you could actually have the front of the unit hit multiple summits before the base of the unit actually clears the first summit. So for that reason, what this does is it registers all these summits along the way and ensures that the unit actually clears these summits before it starts trying to descend. That's basically it. Obviously this is only needed because we are having only 3 points to sample from. If you're using more accurate casts, such as a sphere cast, for instance, this is obviously not required because it would be accurate no matter what. So that's how you implement a different type of height sampler or unit height provider. Now in order to actually attach this to your unit, the first thing you do, as we saw, you actually select custom. And then the second thing you do when you have created your own provider is you actually need to tell the default height navigator that what provider you actually need to use. To do that, you will need to create a mono behavior that implements this interface. This is super simple. So what you simply do is that simply implement this method, and in that method you return an instance of the provider you just created. That's it. So that's basically all there is to it. Admittedly, this is one of the more advanced extension points in Avix Path. The complexity of this obviously depends on what you want to achieve. But I hope this made sense for you. So that's it for now, and see you in the next video.